Hello again. So this is section 10.1, systems of linear equations in two variables. So in this unit, we're going to be looking at some different systems of both equations and inequalities, and then we'll look at some linear equations and then some nonlinear equations also. Okay, so this first section specifically focuses on systems of linear equations in two variables. Now, when we say a system of equations in general, what we're referring to is a set of equations that involve the same variables. Okay, so we're going to be looking at linear equations in terms of x and y, okay, and that's why they have the same variables. And we're going to be looking at them together now on the same graph, and then also algebraically to determine what the solution to those systems would actually be. Okay, now a solution to a system then is an assignment of values for the variables that make each equation in the system true. Now we're going to start with two equations, and we're going to work up to even 3 and 4 and maybe even 5 equations. And we're looking for the values of x and y in this case because it's linear, that would make those systems or all of the equations within the system true statements. Now, one of the methods we can use for this is what's called the substitution method. Now, our steps for doing that, the first step is we're going to solve for one of our variables, right? And it doesn't matter whether you solve for x or y. We're typically going to look at the equation and decide which one looks easier to solve for, and that's the one we'll solve for first. Once we know the value of that variable in terms of the other, then we can substitute that into the other equation. And when we do that, that's going to get us a single variable in that equation that we can then solve for. And then our last step is going to be what we call back substitute, where we take the value of that variable now, plug it back into either one of the equations, and that'll give us the value of the other. All right, so example 1, we want to find all solutions of this system. And we're going to use our substitution method that we just talked about. So again, the first step is to take one of your equations and solve for one of your variables. Now, if I look at these two equations, the easiest variable to solve for is this y right here, right? Because it's just a y to the first power, has a coefficient of 1 already. So I'm going to take that equation there, 2x plus y equals 1, and I'm going to solve for y. So I'm just going to subtract 2x from both sides. And that's going to give us y equals negative 2x plus 1. And again, it does not matter which variable you solve for first or which equation you start with, okay, but I always look for the one that looks easiest to solve for. Now that we've got that, we're going to take that value for y and we're going to substitute it into the other equation. And that's the key. It has to go in the other equation. So we're going to say 3x plus 4 times. And now instead of y, I'm going to replace it with this negative 2x plus 1 that I just found here. So we've got negative 2x plus 1, and that's going to equal 14. So again, because y is now equal to negative 2x plus 1, I can substitute that in place of y in the other equation. Now I have an equation that's just in terms of x, and I can solve for x. So we'll distribute the 4. That gives us 3x minus 8x plus 4 equals 14. Combine your like terms. 3x minus 8x is a negative 5x plus 4 equals 14. Subtract your 4, negative 5x equals 10, and divide by negative 5, x equals negative 2. Now, be careful, we're not done yet. And the reason is we're looking for the solution to this system, meaning we need an x value and a y value that would make both of these equations true. So once I find that x value, I still need to go back and back substitute to figure out what y is. Now, it doesn't matter which equation you plug into. And honestly, the easiest place to substitute this time is going to be this equation that we've solved for y already. So right here, I'm going to say y equals negative 2 times our x value, which is negative 2, plus 1. Now, if we simplify that, negative 2 times negative 2 is positive 4. 4 plus 1 is 5. And so now we have a y value of 5. Now, in general, when we find these solutions to systems, we're going to have an x and a y value. Eventually, we might even have more variables, so we might have an x, a y, and a z. We're going to write them, in this case, as ordered pairs. So we're going to say this is negative 2, positive 5, and this right here is our solution now. So since we have an x and a y value, we can write it as an ordered pair as a point. So negative 2, 5 is our solution to that system. Now, another method we have for solving these systems is what's called elimination. So if we want to use the elimination method, the first step is to adjust the coefficients. And what we mean by that is we want two of our terms in different equations to actually have opposite values so that they will end up canceling out. So if I have like a 5x in one, I need a negative 5x in the other. Or if I have a 2y in one, I would need a negative 2y in the other to cancel it out. Okay, and so we're going to multiply one or both equations by some value so that we can make that happen so that those things actually cancel out. All right, once we have those set up, then we can add the two equations together to make that cancellation happen. Then once we do that, we'll get rid of one of our variables. We can solve for the other. And once we know the value of that one, just like substitution method, we're going to back substitute into either one of our equations, and that'll give us the value of the other variable. All right, so example 2, again, we're going to find all solutions, but we want to use the elimination method this time. Well, if I look at this one, right off the bat, I notice I have a positive 2y and I have a negative 2y. So I don't need to adjust my coefficients this time because just adding these together, my y terms are going to cancel. So my first step this time is just to add these two equations together. 3x plus x is going to give us 4x. My 2y plus negative 2y is going to cancel out. And on the other side of my equals, I have 14 plus 2. That's going to be 16. Now I can just divide by 4 to get x by itself, so x equals 4. Once we have that, now we can back substitute. And again, it does not matter which equation you plug into. Both equations will give you the same y value. I'm going to use this bottom one down here, and I'm going to say 4 minus 2y equals 2. Now I'm going to subtract my 4 on both sides. It's going to give us negative 2y equals negative 2. And if we divide both sides by negative 2, that should give us y equals 1. And then again, just like with the other method, we found an ordered pair because we have an x and a y value. So we're going to write it as a point, 4, 1, and that is our solution. Now again, if those terms didn't already match up so that they would cancel, then we would need to multiply either one or both equations to make those terms cancel out. Okay, but in this case, they gave us equations that already cancel one of our terms, so we just go ahead and add them together. All right, and then the graphing method. Okay, so this is our third and final method for solving these systems of equations in two variables. All we're going to do is graph each equation. And when we do that, we're going to need to solve for y if we want to put it in a graphing calculator. If you're using Desmos, obviously you wouldn't even need to do that because you can actually just graph equations in Desmos without solving for y first. But then we're going to look for the intersection points. So those 2 points that we found on examples 1 and 2 using substitution and elimination, that point that we found, those are the intersection points of those two lines. Okay, and so graphing, that's what we're looking for now. Okay, so we have 3 different methods now to find that point of intersection, which is the solution to our system. Okay, now this time, notice this is not a good equation for elimination or substitution because solving for one of the variables is going to be difficult. Multiplying to make one of the variables cancel out is also going to be difficult. So whenever you have decimals and things like that, you're probably going to want to use graphing. Okay, so I'm just going to put this into Desmos now. And then we'll look for that point of intersection. So our first equation here, we have 1.35x minus 2.13y equals negative 2.36. Then our other equation, we have 2.16x plus 0.32y equals 1.06. Again, if you didn't have access to Desmos and you were using a graphing calculator instead, you would need to solve each one of those equations for y. Just isolate y in both so that you could actually graph it. Okay, but you should get those same lines regardless. Then we're going to find our point of intersection. And notice in Desmos, it's pretty easy to do that. We're just going to click on the point where they intersect. And so you can see here, if we keep 2 decimal places, because that's what the original equations had, that would give us 0.30 as our x value and 1.30 as our y value. And that's all there is to it if we're using the graphing method. Okay, so You're going to need to know how to do all three methods for a test, okay? But just know that on your homework, right, whichever method looks the most convenient and easiest, feel free to use whatever method you want. Just make sure you're familiar with all three by the time you actually take your test. So there you go. So that would be our solution this time. Again, it's an ordered pair because we had an X and a Y value. And so we would just say 0.30, 1.30 is the solution to that system this time. Right, now, the number of solutions of a linear system in two variables. So for any system of linear equations in two variables, one of these situations has to be true. Either we could have exactly one solution, and that's what we've looked at so far. All three of the examples we've done had exactly one solution, one ordered pair, okay, that was the point of intersection of those two lines. We could also have a situation where we have no solution. And if you think about it, right, since we're graphing two lines now, the only way that it would have no solution is if those two lines never intersect, meaning that those lines would have to be parallel. Okay, so that would be the second option. The third option is that we have infinitely many solutions, meaning that they overlap at every single point along that line. In order for that to be true, they have to be the same line. Okay, so either we have two lines that intersect at a single point, we have two lines that are parallel and never intersect, or we have two equations that give us the same line, and therefore we have infinitely many solutions. All right, now just some terminology. If a system has no solution, then we call that system inconsistent. And if we have infinitely many solutions, then we would call that system dependent. Okay, so just make sure you're familiar with those terms in case you see them. I'm not going to ask for them on a test, but in case you see them in the homework or something, that's what those terms mean. And so here's graphically what we mean by each one of those situations. So again, one solution means we have one point of intersection. That's that first graph. We could also have parallel lines that never intersect. That would be the second graph. That's no solution. Or we could have two lines that coincide. They're right on top of each other. They're the same line. And that's going to give us infinitely many solutions. All right, so we want to solve the system and graph the lines here so that we can see what the solution is. Now, it doesn't matter what method we use. So I'm going to use elimination here just so we can get an idea of how this would work if the variables don't already match up. So I'm looking here. I've got a positive 2y in my second equation. I've got a negative y in my first. If I want those terms to cancel out, I could just multiply this top equation by positive 2, because that would give me a negative 2y that would then cancel out the positive 2y in the other equation. If I distribute then, that's going to give us 6x minus 2y equals 0. And then our bottom equation, we're going to keep exactly the same, 5x plus 2y equals 22. So this is an example where I just need to multiply one of the equations by something to make those variables cancel. Okay, and again, you're allowed to multiply both equations if you need to. So just look for what variable looks like it might be easy to multiply to cancel out another one. In this case, just multiplying the top equation by 2 cancels out the y's for us. So now we can add. And when I do that, 6x plus 5x is 11x. My y terms cancel out. And on the other side, 0 plus 22 is 22. Now we can just divide to get x by itself. So if I divide by 11, that's going to give us x equals 2. Remember, at that point, we need to back substitute, so we can go back to either one of our equations and plug in that value. I'm going to go back to the original top equation here and say 3 times 2 minus y equals 0. Well, 3 times 2 is 6, minus y equals 0. And now I can really just add the y to both sides to get 6 equals y. You could have also subtracted the 6 and then divided by the negative 1. It would still give us y equals 6 either way. Okay, so now we know our point of intersection is at 2, 6, and that is our solution to the system. Now it does ask us to graph. I'm actually going to go to Desmos and graph these, and then we can actually check to make sure that the point that we found is indeed the point of intersection. Okay. So our equations this time, we had 3x minus y equals 0. We had 5x plus 2y equals 22. We can see that they do intersect at a single point right up here, and that point is 2, 6. That's the point that we found using our elimination method. Okay, so we know we did our steps correctly. So feel free to use the graph to check yourself, even on the problems where you're asked to use a different method. All right. So again, we want to solve this system. And again, it doesn't matter what method we use. They don't tell us which one we have to use this time. So I'm going to go with elimination again, because this time I have one where I could actually multiply both equations by something to make one of my variables cancel out. Again, it doesn't matter which one we eliminate. I'm going to go for the x this time. So I'm going to look at this top equation here, and I'm basically looking for what would I need to turn the 8 and the negative 12 into so that they would cancel? Well, I know that 8 goes into 24, and I know that negative 12 will go into 24 also, so that's what I'm going to go for. So I'm going to multiply this top equation by 3 so that I get 24x, and that means I need to multiply the bottom equation by 2 so that I get a negative 24x down there. So now we're going to distribute. That's going to give us 24x minus 6y equals 15. In the bottom equation, we get negative 24x plus 6y equals 14. All right, now that we have our new system, now we can add. Well, we are eliminating the x's, so 24x minus 24x, that cancels, that's 0. But notice this time, negative 6y plus 6y is also going to cancel out. So we're really going to end up with 0 on this side, and then 15 plus 14 is going to give us 29 on the other side. Right, now, in this case, if all of our variables cancel out, we have one of two situations. Either we have no solution or we have infinitely many solutions. If you get a false statement, then we're going to say there is no solution. And if you get a true statement, then we're going to say that there's infinitely many solutions. Well, 0 is not actually equal to 29. This is a false statement. Therefore, we would say that this system has no solution. Now, what that means is that if we were to graph these two lines, they should be parallel to each other. And so we could actually check this in Desmos to make sure that we actually have parallel lines. So that's what I'm going to do now. Switch over to Desmos just to check ourselves. So we have 8x minus 5. We're going to have negative 12x plus 3y equals 7. And we can see there on the graph that we do indeed have parallel lines. They're never going to intersect. We're not going to have a point of intersection. Therefore, there is no solution to that system. All right, so now we have a new system. Again, we want to solve. It doesn't matter which way we solve it. I'm going to use substitution this time just to use that one more time. So I'm going to take this top equation here. I'm going to try to solve for x. So we'll have 3x minus 6y equals 12. I'm going to add the 6y, so that's going to give us 3x equals 6y plus 12. And I'm going to divide by 3. Now remember, when I do that, I need to divide every single term by 3. So we're going to have x equals 2y plus 4. And again, if you wanted to use elimination on this one, that's perfectly fine also. It doesn't specify what method we have to use, and all methods will give us the same answer. Now that I know what x is equal to, I can substitute that into my other equation. Okay, and again, that's the key. Don't plug it back into the one we just solved. It has to go in the other one. We're going to have 4 times, at x value, 2y plus 4 minus the 8y equals 16. Distribute. It's going to give us 8y plus 16 minus 8y equals 16. combine like terms, 8y minus 8y cancels out. So we're left with 16 on this side equals 16. Again, all of my variables canceled out, which tells me I either have no solution or infinitely many solutions. Well, in this case, I actually have a true statement. 16 is equal to 16. So that tells me then that this is actually infinitely many solutions. So in other words, these two lines are the same line. They will intersect everywhere. And again, if you want to check yourself, we can look at Desmos just to make sure they are indeed the same line. Switch over there. So we have 3x minus 6y equals 12. And our other line was 4x minus 8y equals 16. And you can see I'll turn one off. You can see that black line is the first one. The red line is the second one. Okay, and they are on top of each other. Okay, so they are the same line. That's why we get infinitely many solutions this time. All right, now some guidelines for modeling with systems, right? So we can actually use systems to help us solve real world problems. First thing we want to do is identify our variables, right? So we're going to figure out what are we actually trying to solve for and label those variables. Then we're going to express all the unknown quantities in terms of those variables. Finally, we can set up the system and then solve it, right? And we can actually interpret those results once we know the solution to the system. Okay, but the real key difference here now with the real world problems is figuring out what you're looking for, defining those variables so that you can set up the system. Once we set it up, we're going to solve it the same way we've been solving the other ones. So a woman rows a boat upstream from one point on a river to another point that's 4 miles away in 1.5 hours. The return trip going with the current takes 45 minutes. We want to know how fast does she row relative to the water and at what speed is the current flowing. Okay, so we've got basically a situation where a woman's rowing a boat upstream and the current's pushing against her. Then she comes back downstream. It's helping her out. We want to know how fast would she be rowing in this situation and how fast is the water moving, which means we have two different variables that we're solving for. So I'm going to set this up as x is the woman's rowing speed. And then I'm going to let y equals the speed of the current. Okay, so those are the two things we're asked to find. So we know those are going to be our two variables this time. So that's what it means by define those variables first. Now we need to set up equations. And remember, we're going to need two equations because we have two variables we're trying to solve for. Those two equations, I'm going to use the formula that rate times time is equal to distance. So I know in this case that when she's going upstream, it's going to take her 1.5 hours to get there. And I know in this case that the speed of the current is actually working against her, right? So I know we have her speed minus the speed of the current is going to be the actual rate that she's moving. So we're going to say x minus y is the r value. We're going to multiply that by time. Now, it's up to you if you want to keep everything in hours, we can, or you could actually put everything in minutes. I'm going to keep everything in hours, and I'm going to use 1.5 here. And that's going to be equal to her distance, which is 4 miles. So that's our first equation. Now, the second equation, when she's coming downstream, the current is actually helping her, and it's going to speed her up. So we're going to take her rowing speed plus the speed of the current. That's going to be the rate that she's actually traveling. We're going to multiply that by the time. Notice here we have 45 minutes in the other direction. I need this to all be in the same unit of time. 45 minutes is 3/4 of an hour, so I'm going to use 0.75 here as my time. And then the distance is the same distance of 4 miles. So here is our system this time. Now we need to solve, right? So we can use any of our methods that we want to. First thing we need to do, though, is distribute so that we can actually get this to look like the equations we had in the past examples. We're going to have 1.5x minus 1.5y equals 4. And down here we'll have 0.75x plus 0.75y equals 4. Now, I notice here that I can easily multiply one of these equations and use elimination. But again, if you want to use substitution, that's fine. If you want to graph, that's fine, right? You could do that too. I'm just going to multiply this bottom equation right here by 2, and then I can use my elimination method. If I do that, we're going to have, keep the top equation, 1.5x minus 1.5y equals 4. Down here, then, we're going to have 1.5x minus 1.5y equals 8. Oh, sorry, this should be a plus. Now, when I add these two equations together, I'm going to end up with 3x. My y terms are going to cancel, and then we're going to have 12. Divide both sides by 3, and we have x equals 4. Okay, so now we know the woman's rowing speed, right? So we know that x equals 4, and now we interpret it in terms of the context of the problem. Well, we know our speed in this case is going to be measured in miles per hour, since we left our time in hours and our distance was in miles. So this is 4 miles per hour for the woman's rowing speed. Now we need to find the speed of the current. So again, I'm going to back substitute, and it doesn't matter which equation I use. I'm just going to use the top one here. I have 1.5 times 4 minus 1.5y equals 4. 1.5 times 4 is 6. Minus 1.5y equals 4. Now we're going to subtract, so we'll have negative 1.5y is equal to negative 2. And then we divide. So we do negative 2 divided by 1.5. Should give us 4/3. And again, in terms of the context of the problem here, it's going to be 4/3 miles per hour, okay? Or 1.3 repeating if you prefer the decimal. But again, in WebAssign, if you're looking for exact values, you would need to leave that as a fraction. All right, so that's all we've got for that section. As always, let me know if you've got any questions. Send me questions in WebAssign as you have them. Come and see me during student hours if you need to. Have a great day, and I will see you next time.